As more infrastructures continue to be built across the world, construction will continue to require the assistance of geotechnical engineers to identify how the soil found at building sites need to be modified. Most soils inherently possess various limitations in terms of withstanding loads, so soil improvement techniques need to be applied in order to increase the soil's strength, reduce compressibility, and/or enhance their overall performance. Soil improvement is an engineering technique used to fix soil properties. It's important to know what type of soil foundation is being altered, as the deeper the soils are located, the more work is required to fix said soil. For this reason, the main type of soil that will be discussed here will be deep soils. For further specification, the methods discussed will also be limited to those most commonly used to treat clay soils. Some of these methods will involve physically altering soil by means of drains or vibro replacement. Others will involve chemically altering soil by mixing in additives such as grout or lime. Prefabricated vertical drains, or PVDs, are drains that act as a conduit for water to dry out a variety of construction locations. PVDs insert into groundwork with the assistance of a device called a mandrel. This mandrel rolls over the ground being built on using an excavator and inserts into the soil at set intervals. The water in the soil is then discharged out and directed away from the site. The new soil then has increased strength, an accelerated consolidation process, reduced settlement, and reduced pore water pressures. Vibro replacement displaces soil with the use of vibrators hung and lowered from a crane. Once at a desired depth, soil is then densified as the vibrator is raised back up. This densification results from energy exerted from vibrations as they reduce the intergranular forces between soil particles and stiffen minerals. As the vibrator is retracted, gravel runs from the tip of it into the space created. This gravel is then compacted to form a stone column. This method helps minimize effects of liquefaction and creep, as well as increased soil friction angles. One of the more popular chemical additives to mix into soil is lime, which then creates an improvement technique called lime stabilization. This offers a more economical means of improving clay without needing to pay for aggregates. This helps increase soil stability by reducing swelling potential. It also enhances properties such as resilience, water content, and shrinkage limage. Changing these weaknesses allow clays to resist being deformed due to fatigue or fractures. However, when adding lime to clay soils, it's important to note what type of clay is being manipulated. The two types of clay most commonly encountered are montmorillonite and kaolinite. Kaolinite has lower tendencies for swelling than most clays, as well as lower plasticity levels due to it having low levels of silica in its genetic makeup. These clays are commonly found in hot, humid regions with high precipitation. Montmorillonite is more prone to swelling than most clays and exhibit higher plasticity due to its spread-out molecular structure. These clays prefer cooler, damp climates that make it difficult to drain and clump. The addition of lime helps decrease plasticity in montmorillonite greater than kaolinite due to its ability to help soils repel water. It also reacts faster with montmorillonite in terms of increasing strength. That said, kaolinite gains more strength by comparison after having longer times to cure with lime. The final method discussed will be grouting. Grouting is attained by ejecting cement at high flow rates and pressure into soils to create a solidifying mixture that helps improve soil stiffness. Calcium chloride and sodium silicate are also viable options for grouting material, as these materials present advantages such as being non-toxic, cost-effective, and risk-free of contamination. Grouting can be subdivided into three categories depending on the type of work it is used for. Jet grouting is the most common method that is used for basic foundations. Compaction grouting is often used to keep settlement from underground construction under control. This then provides help for stabilizing sinkholes. Fracture grouting is the most uncommon method. It typically involves injecting grout at an angle where it can be pumped directly underneath unstable structures. PVDs are widely considered to be the best low-cost solution for improving soils due to being a simple and fast method to perform on site. That said, these drains present the danger of possibly harming underlying aquifers if not handled correctly. Also, reliable consolidation rate predictions are difficult to obtain, which presents the risk of producing uncertain results after application. Fiber replacement is an economic and flexible method that can adapt easily to fit the needs of varying ground conditions, making it multi-purposeful. However, fiber replacement requires highly qualified experts to execute it, making it a restrictive method. It also only offers a temporary means of improvement. Line stabilization is a widely used improvement method that enhances many favorable engineering properties. It's a fairly simple procedure that saves construction costs, promotes sustainability, and conserves soil nutrients. A major con involved with mixing lime into soil is that it requires a large attentive team to ensure the lime doesn't harden too quickly. Grouting benefits from only requiring a small amount of space to perform the job. This process can be relatively expensive, but the multiple improvements that come with using this method can potentially come out being cost-effective. That said, when cement grout is used, it requires ample amounts of time to set and cure with the soil. Another disadvantage is the need to continuously flush the ground treated to prevent future fractures. This concludes the discussion of various soil improvement techniques and what each one has to offer. The decision of which method is best to use depends on how much the soil has to change to fit the needs of a project, as well as how well the presented benefits outweigh the costs of each method. It is an engineer's job to weigh in all of these factors and make the final call that ensures a project can proceed building with little to no changes made to the final structure. Thank you.